Let's talk about confidence interval. So what's the concept? The concept is we are trying to get a probability with a lower limit and upper limit for theta. So L stands for lower, U is upper, so that the area in between is 1 minus alpha. So theta here, unknown population parameter. And 1 minus alpha is known as the confidence coefficient. So this is theta hat L and theta hat U are called two-sided confidence interval. So there must be something called one-sided. Yes, there is one-sided confidence interval. I'm just writing CI. CI stands for the confidence interval, or we call it confidence bound. So there is a confidence interval and there is a confidence bound. There are two different concepts. So what are the confidence bound? There are two of them. One is if this is equal to 1 minus alpha. So this is written as this way, theta hat. So this means that included, and the lower limit is infinity. This is what we call the lower confidence bound. Similarly, if we have theta that's equal to 1 minus alpha, that is what we call, so that's denoted by minus infinity and theta hat U and then close bracket. This is upper confidence bound. So that's pretty much the concept. Both confidence interval and confidence bound. All right. So let's add to this a normality assumption. If I add a normality assumption, how that will look like. So when I'm adding normality assumption, it's same thing as when we normalize it. Same thing as saying if x bar follows normal mu sigma squared over n, then x bar minus mu over, actually the theta hat will go here, x bar minus mu divided by sigma over square root of n, that will follow a normal 0, 1. So this, I can write this as negative z alpha over 2 less than equal to z less than equal to z alpha over 2. That's 1 minus alpha. It's saying this is the normal distribution. This area and this area both are alpha over 2. And this is 1 minus alpha. So the whole area is 1. This point right here is z alpha, negative z alpha over 2. This point right here is z alpha over 2. And that's pretty much what it is. Now I can replace this z, so I'm writing right here. I'm replacing this z by this expression right here. Theta hat minus theta over sigma theta hat. And that's equal to 1 minus alpha. Now if I do a little bit of manipulation here, a little bit of math, that will give us theta hat minus z alpha over 2 times sigma theta hat less than equal to theta less than theta hat plus z alpha over 2 times sigma theta hat, which is equal to 1 minus alpha. And this is, so the lower limit, this is the theta hat L, This is the theta hat u, and this is what we call 100 1 minus alpha percent confidence interval. So this is the formal definition of the confidence interval if the normality is our assumption. Now you can ask that, okay, what's going to happen if it's a confidence bound? Well, if it's a confidence bound, then we're going to write this, so 100 1 minus alpha percent confidence bound. The lower bound, that will be theta hat L equal to theta hat minus Z alpha. Remember, this is alpha, not alpha over 2 anymore. Sigma theta hat. And theta hat U, of course, is infinity. For upper bound, theta hat L is minus infinity. And theta hat U, that would be theta hat plus Z alpha sigma theta hat. Let's try some example. This example is in your book, 8.7. N is 64. X bar is 33 minutes. S square is 256 minutes. So we want to find a 90% confidence interval. All right, so 1 minus alpha, that's 0.9, alpha 0.1, alpha over 2, 0.05. So what we are looking for, essentially a z 0.05 first, which is 1.645 from the table. And the confidence interval, which is x bar plus minus z 0.05 times s over square root of n. So this is given as 33 plus minus 1.645 times s is given as square root of 256, which is 16, divided by 64 square root of that is 8. So it's 33 plus minus 1.645 times 2. Now I do need two numbers here. So 33 minus this you will write here. 33 plus this you will write here. So I need as answers two distinct numbers. I do not want this as the answer. I want the math to be done, the arithmetic to be done and written down here. Okay. So let's try the next one, 8.8. Here in this case, the formula for the confidence interval is P1 hat minus P2 hat plus minus Z alpha over 2 times square root of P1 hat Q1 hat divided by N1 plus P2 hat Q2 hat divided by N2. So this is your formula. Everything should be given to you. For example, P1 hat, that is 12 over 50, which is 0.24. P2 hat, that's 12 over 60, which is 0.2. Similarly, Q1 hat is 1 minus 0.24, which is 0.76. Q2 hat is 1 minus 0.8, which is 0.2. So I know every information here. What I'm looking for, 98% confidence interval. That means 1 minus alpha is 0.98, alpha is 0.02, alpha over 2 is 0.01. So Z 0.01, that number, again, you get that from table, is 2.326. Now it's a matter of plugging in all the numbers. 0.24 minus 0.2 plus minus 2.326 times 0.24 times 0.76 divided by 50 plus 0.2 times 0.8 divided by 60, and whatever the final answer is. Now for 8.7, this question right here, for 8.7, this question right here, for this question, if I'm looking for a confidence bound, so everything else is right here, just we are looking for a lower 8.7, a lower confidence bound. What would be the change in the calculation? So for the same question right here, if I'm looking for a lower confidence bound, what would be the calculation change? Well, the only thing that changes is right here. 1 minus alpha is 0.9, alpha is 0.1, so we are looking for z.1 from the table, which is 1.282. And then the lower bound, lower confidence bound will be x bar minus z alpha times s over square root of n, which is 33 minus 1.282 times 2. So that's the only change here in the calculation. This is the only change. We are using a different z value. This is the new z value for confidence bound. So I'm looking for confidence bound. That's the new z value. That's the only difference here. All right. Now this is kind of a concept that I'm going to explain that in terms of an example. The example is, so the normality is not a must. We can find a confidence interval from any distribution. For example, y is following exponential distribution with theta. Theta is the unknown parameter. Now, y divided by theta, this is I'm defining as u. So the distribution of u, that will be e to the power minus u. Probability of a less than u less than b is 0.9. So if I try to draw this, this is the exponential pretty much, and I'm kind of pretending that this area and this area, these two are 0.5. I'm sorry, 0.05. 0.05. These two areas are 0.05. The middle area is 0.9. So that's the same thing as saying that probability u less than a, which is from 0 to a, e to the power minus u du, this is 0.05. And probability of u greater than b, which is now from b to infinity, e to the power minus u du, that's 0.05. This is what we know. So this is I'm denoting, this equation I'm denoting by 1, this equation I'm denoting by 2. So from 1, I can write 1 minus e to the power minus a as 0.05. A should be then 0.051. From 2, e to the power minus b equal to 0.05, which gives us b equal to 2.996. So essentially what we did here, probability of 0.051 less than equal to u less than equal to 2.996 is equal to 0.9. Since we know the distribution, what is y, we are defining something as y over theta. That confidence interval can be calculated by integration. That's the whole point here. Now, if you want that, okay, I want a confidence interval of not u, but theta, because theta is an unknown parameter. Why we can get random samples? Well, you can do that too. So I'm just skipping it here. So you remember this, so that's what I'm writing again here. Probability of 0.051 less than equal to u less than equal to 2.996. That's equal to 0.9. That's what exactly I have here. I just wrote it down here. Now the reason I'm writing this u, I already defined that. That's y over theta. So I can have a theta confidence interval here, which will be y divided by 2.996 and y divided by 0.051. If I know y, which is, I'm going to collect the random samples and I know what's the value of y, I can actually find this. So that's the whole idea. Well, what I'm going to do is let me see if I can assign a few homework problems here. This is homework number 4, because I decided the homework 3 ends with those 19 problems. So homework 3 will be due soon. We're going to decide when. This is homework 4. I'm adding more problems. Homework 4 starts from these set of problems: 8.40, 8.41, and 8.43. But I'm planning to add more problems to this. 8.57, 8.59, 8.61, 8.63, and 8.65. I need one more lecture, which is a sample size, how to select sample sizes. So sample size calculation, that will be the next lecture on. After that, I'm going to add 2 more problems to this. So sample size calculation, that would be our next lecture video. But pretty much from here, the homework 4 starts. All right.